All right, let's talk about something really cool. Have you ever wished you could just give your applications a brain? Imagine our weather app. It works perfectly. But what if your users could do more? What if they could just ask in plain English, hey, what's the weather like in Tokyo, and is today a good day for a picnic? And your app could actually understand and reason about that. Well, today we're going to dive into how to make that a reality using AI agents and an incredible framework from JetBrains called Koog. It's way easier than you might think. Let's first see what an AI agent is. An AI agent is action oriented. You give it a goal and it goes off and does a whole bunch of tasks to make it happen. It's the difference between asking for a recipe and having a chef actually cook the entire meal for you. There are four qualities that help build strong and reliable AI agents with Koog. Each block highlights a different pillar. First is predictability. This refers to how consistently the agent behaves. When inputs are similar, the agent should respond in a stable, reliable way. It helps you trust the system and makes debugging much easier. Second is fault tolerance. This is about keeping the agent functional even when something goes wrong. That might be a model error, a missing piece of data, or any unexpected condition. A fault-tolerant agent doesn't crash, it recovers, retries, or gracefully handles the issue. Third is Kotlin idiomatic rise. This highlights the idea of writing agent logic in clean, expressive Kotlin. Instead of forcing complex patterns, you use Kotlin's natural strengths like extension functions, coroutines, sealed classes, concise syntax, and strong type safety. It leads to cleaner and more maintainable agent code. Last but not least is comprehensive AI development. This means the focus isn't limited to just the agent part. A real system often needs extra pieces like data processing, reasoning steps, tool execution, UI integration, or follow-up workflows. The idea is to support full end-to-end AI tasks, not just prompt handling. Next, let's jump on understanding the Koog architecture. It really just boils down to three core pieces that fit together beautifully. First up is the environment. And don't let the fancy names scare you. The environment is just your app. It's the code you've already written. For your weather app, it's your data module with all its API clients. It's your domain module with all the business logic. It's the world the agent gets to play in. Second, you have the agent logic, which code calls a strategy. This is the brain of the operation. It's the playbook. It's where you define the workflow for how the agent thinks and makes decisions. Should it call a tool now? Should it ask the user for more info? You control all of this, which is so important for making the agent predictable and, actually testable. And the final piece of the puzzle is the LLM connection. This is where the raw intelligence, the reasoning power, comes from. Koog makes it incredibly simple to just plug into powerful models like GPT-40 or Llama 3. This gives your agent the smarts it needs to figure out which of your tools it should use and when to use it. Next, we need to understand how an AI agent works with an LLM in a loop and how tool calls fit into that process. On the left side, you see the agent LLM interaction cycle. It starts with user interaction. The user sends a request to the agent. The agent is the middle layer, not the LLM itself. Next is LLM communication. The agent forwards the request to the LLM and gets a response back. At this stage, the LLM might just generate text or suggest that some action is needed. Then comes response processing. The agent inspects the LLM's response and decides what to do. Is this a final answer for the user? Or does it require calling a tool like an API, database, file system, or calculation? If a tool is needed, the flow moves to tool execution. The agent invokes the required tool in the environment. This is where real work happens outside the LLM. After that, result feedback kicks in. The environment returns the result of the tool execution back to the agent, which then sends it to the LLM so it can reason over the new information. This loop can repeat multiple times until the agent produces a final answer for the user. We're going to properly understand what tools mean in Koog, why they matter, and how @tool and LLM description make the LLM behave like a real agent instead of a confident guess machine. First thing, we're not talking about tools, as in Gradle tools or IDE tools. In Koog, a tool is simply a Kotlin function you allow the agent to call. That's it. The trick is, the LLM does not directly execute code. It can only generate text. So if you want your agent to do something real like hit an API, look up a database record, compute something accurately, read a file, or check system state, you give it tools. So think of the agent as a manager. The user asks for something. The agent asks the LLM to plan. If the plan needs real-world data or real computation, the LLM says, call this tool with these inputs, and the agent runs your Kotlin function and feeds the result back. Koog supports different ways to register tools, but annotation-based tools are popular because they keep your code clean. Now, let's look at the actual steps to build and run an AI agent. We'll go bottom to top because that's how you actually build it. First step, define and register tools. This is where everything starts. Before the agent even talks to an LLM, you define what it's allowed to do. These are your Kotlin functions annotated with @tool. API calls, database lookups, calculations, file access. If the agent can't do something here, it can never do it later. This step defines the agent's real-world capabilities. Next step, set up LLM connection. Here, you choose which LLM you want to use. OpenAI, local model, Ollama, anything supported by Koog. You configure the model, tokens, temperature, and plug it into a prompt executor. At this point, the agent knows how to think, but it still doesn't know who it is or what it's allowed to do. Then comes the configure agent. This is where you define the agent's identity and boundaries. You create the system prompt, you define constraints, you decide how many iterations the agent is allowed to run, how it should behave, and how strict it should be. This is where you turn a raw model into a purpose-driven agent. After that, instantiate agent. Now everything comes together. Tools, LLM connection, system prompt, executor. You combine them into a single AI agent instance. This is the moment where your agent actually exists as a runnable object in code. Then we move to the execute agent. This is where the loop starts. You call agent.run. The agent takes user input, sends it to the LLM, decides whether a tool is needed, invokes it, feeds results back, and repeats until it reaches a final answer or hits a limit. And finally, run with user input. This is the part everyone sees. The user types something, but under the hood, everything you configured earlier kicks in. The agent isn't just chatting, it's reasoning, calling tools, handling results, and responding with context. If you've got the gist of what Koog and agents are, let's stop theorizing and actually plug a weatherbot into our app. The first thing we need is the dependency. When I recorded this, Koog was on 0.5.2, but as of now, the latest release could have changed. So don't just copy my number blindly. Quickly check the Koog docs or Maven Central and grab the newest version. Now open your libs.versions.toml. In the versions block, add a Koog version entry. Then in the libraries block, add the Koog library alias that points to that version reference. Sync the project. Once Gradle sync is done, jump into your domain module build.gradle and add the two dependencies we need. First, the Kotlin serialization plugin runtime, because Koog leans on serialization in a lot of real setups. Second, the Koog agents dependency you just registered. Hit sync again, and now we're ready to start writing the actual bot code. If you've been following the last tutorial, you should already have your weather forecast model sitting inside the domain module. Go ahead and open that class. The first thing we're going to do is annotate it with @serializable. This tells Kotlin that this model can be safely converted to and from structured data, which is exactly what Koog needs when it starts talking to our agent. And don't stop there. Any model that this class depends on also needs the same annotation. So make sure all those nested data classes are marked as @serializable too. Now here's where Koog gets interesting. Earlier we talked about Koog's special annotation called @LLM description. This is the piece that gives the agent more context about what your data actually means, instead of it just seeing a bunch of field names. So for this video, to keep things simple, we're going to start small. Add @LLM description to the moonrise field and the future moon phases field, and give each one a short, human-readable explanation of what that value represents. You're basically teaching the model what these properties mean, and that small bit of context goes a long way. Now it's time to add the toolset part we talked about earlier, so our agent can actually call real code instead of guessing. Open your existing getTodayWeather use case. The first change is simple. Extend this class with Koog's toolset interface. That's basically your this class exposes callable tools marker. Next, find the invoke function. This is the function we want the agent to call, so we'll annotate it with @tool. So Koog registers it as an actual tool at LLM description, so the model understands what the tool does and when to use it. Now here's the important part. In our project, this use case was returning a Kotlin result. The problem is, that's not something we can easily serialize and send cleanly through the agent pipeline. So for this video, we'll keep it practical and do a simple workaround. Change the return type to weather forecast model call.getOrThrow on the existing result tries. So if everything works, the agent gets a clean model back. And if something fails, getOrThrow throws an exception, which is fine for now because it keeps the flow simple and focused while we learn the agent integration. All right, now we're getting into the really exciting part. This is where we stop building pieces and actually create a use case that can take a user's question and turn it into a real answer. First, let's create a brand new use case. This one's job is simple on the surface. It takes what the user types, processes it, and gives back a response. Under the hood, it will depend on our get today weather use case, so it can pull real weather data whenever the agent needs it. The invoke function for this use case will take two parameters. The first one is the user input. The second one is the cache directory path. We're not going to use that just yet, but keep it there. In a minute, you'll see why it becomes really important. Now let's build the agent itself. The very first thing you need is your OpenAI API key. Head over to the OpenAI website, generate your key, and keep it somewhere safe. We'll plug this into our app in just a second. Next, we configure our LLM and executors. We're going to use the simple OpenAI executor, and this is where we pass in that API key. This executor is what actually talks to the language model on our behalf. After that, we register our tools. We already created one custom tool from our weather use case, and we'll also add a predefined exit tool. Once both are registered, the agent knows what real actions it's allowed to perform. Now we create the agent config. Here we define a short system prompt that explains what our weather bot is responsible for, the model, which in our case is GPT 4.1, and the max agent iterations, which we'll set to 10, so the agent has room to think, act, and verify before answering. We're creating a real AI agent. The first big thing we wire into it is a cached prompt executor. That means every time the agent talks to the language model, it does so through a caching layer. If the same or very similar prompt shows up again, the system can reuse the previous response instead of calling the model again. This makes your agent faster, cheaper, and way more stable over time. Then we define the strategy. This is the brain of the agent. Here's what actually happens when a user sends a message. The agent forwards that message to the language model and stores all the responses it gets back. It does not immediately reply to the user. Instead, it checks whether the model is asking for any tool calls. If tool calls are present, the agent enters a loop. This loop means we're not done yet. The agent pulls out the requested tools, checks how large the current conversation history has grown, and if it's getting too big, it compresses the history so it stays safely within token limits. Once the context is safe, the agent executes all the requested tools in the real environment. These could be API calls, database queries, calculations, file operations, or any other real actions you've exposed. The results of those actions are sent back to the language model so it can reason over real data instead of guessing. This cycle repeats until the model finally stops asking for tools and returns a proper assistant message. Only then does the agent extract that final response and return it to the user. Next, because our use case now extends the toolset interface, we need to tell Dagger how to actually create an instance of it. So head into your domain module, open the DI package, and create a new object class called DI Provider. This will be our manual wiring point for anything the agent needs. Inside this object, add a singleton provider function for getTodayWeather use case. In that function, pass in all the required dependencies and return a fresh instance of the use case. Once that's done, do a clean project followed by a rebuild. That forces Gradle to regenerate all the required classes and keeps everything in sync. All right, now let's switch gears and start building the UI for our bot. First, open your app module's build.gradle.kts file. We're going to add two things here. One is the Lottie animation dependency because we want some smooth, lightweight animations in our bot UI. The second is the material icons extended library. Now, quick side note, According to the latest Android guidelines, it's actually better to avoid pulling in the full material icons library and instead add only the vector drawables you truly need. That keeps your APK smaller and your app lighter. For this demo, though, we'll use the library for speed and convenience. Next, scroll down to the packaging block under Resources. Here we're going to exclude a few meta-inf files. A lot of modern libraries, including animation and icon libraries, ship with their own metadata files inside the meta-inf directory. When multiple libraries include files with the same names, Gradle doesn't know which one to keep, and you'll start seeing build errors like duplicate class or duplicate meta-inf file found. By explicitly excluding those files, you're telling Gradle, these metadata files are not needed at runtime, so feel free to drop them. Once that's done, sync the project and we're ready to start designing the bot UI. All right, let's clean a few things up first, then we'll wire the bot screen into the app. First, open current weather view model. Right now, you're probably using fold on success on failure. Let's simplify this. Move that logic into a run catching block and handle the fallback using get or else. Now let's add the bot to the UI. We're going to add one more bottom navigation item, and when the user taps it, it'll open our new screen. To do that, open homescreen.kt, which we created in the earlier videos. Inside the Home tab enum class, add a brand new item for the bot screen. For the icon, I'm going to use a vector asset I downloaded from an open source pack, but you can absolutely use any icon you like. Once that's added, go into the home screen composable. You'll see the when block that switches between screens based on the selected tab. Add the missing branch for the new tab, and when it's selected, we'll open Weather Agent screen. Cool. Navigation is ready. Now we build the feature. Inside your feature package, create a new package called Weather Agent. And inside that, we'll start with the contract file, Weather Agent Contract. Same pattern as all the other screens we've built so far. For the messages, create a sealed class. We'll support 3 types: user message, when the user types and sends a query; agent message, the response coming back from the agent; error message, in case something fails. Now the UI state. Keep it simple and focused. Create a data class that holds a list of messages, this is what we render in the chat, the current input query from the user, and a Boolean loading flag that tells the UI when the LLM is processing the request. And finally, events. We only need 2 to start. One event for when the query text changes, and one event for when the user hits send or presses enter. That's the full foundation. Next, we'll build the view model to wire these events to the agent call. This view model is managed by Hilt, so we don't manually create anything. Dagger handles the whole thing for us. It injects 2 key dependencies. First, the use case that knows how to talk to our agent, and second, the application instance, because we need safe access to things like the cache directory. And that's exactly why this view model extends Android view model. We're not doing it for fun. We need application level context, and this is the clean, correct way to get it. Inside the view model, we store our entire screen state inside a state flow. This state is basically the single source of truth for the UI. Messages, input text, loading status, everything the screen needs lives right there. We keep the mutable version private, and we expose a read-only flow to the UI. So the UI can observe changes, but it can't accidentally mess with the state directly. That one detail alone saves you from a ton of weird bugs later. Now, every user action comes through one function, one entry point, nice and predictable. When the user types, we don't do anything fancy, we just update the query in the state. When the user hits the ask button, though, that's where the real flow starts. First, we validate. If the query is empty, we don't do anything. But if it's valid, we immediately do 2 things. We append the user's message to the message list, and we clear the input field. That small detail is huge. It gives instant visual feedback, so the UI feels fast even before the agent responds. Now we launch a coroutine in view model scope. Inside that coroutine, we flip the loading flag to true, and then call our use case. And remember, this use case isn't just a basic API call. It runs the full agent pipeline. That means tool calling, looping, verification, caching, all of it. And we pass it 2 things, the user's query and the cache directory path, so it can store and reuse results when possible. Once the agent finishes and we get a final answer back, we update the state one last time. We add the agent's message to the chat list, and we turn off the loading flag. And the best part? We don't manually refresh the UI anywhere. Compose just reacts. The state updates, the UI updates, the loading indicator disappears, and the answer shows up like a real chat experience. All right, now let's bring the chat UI to life. First, create a new Kotlin file called Weather Agent Screen. This is where our bot screen starts taking shape. Inside this file, we're going to define 3 small compose components. Each one represents a different role in the conversation, and each one has its own visual identity, so the chat feels natural and easy to read. The first component is the user message bubble. This one is aligned to the right side of the screen, so it immediately feels like this came from me. We give the container a maximum width so long messages don't stretch awkwardly across the whole screen. Rounded corners give it that soft, familiar chat bubble shape. For the background, we use a horizontal gradient made of 2 purple-pink tones, which gives user messages a clear visual personality. Inside the bubble, we simply render the text using our custom text component. The second component is the LLM message bubble. This looks similar, but it's aligned to the left side of the screen, so it clearly reads as "this came from the assistant." The corner rounding is slightly different, which means even without colors, you could still tell which side is which. It also uses a gradient background, but with a deeper purple palette, giving assistant messages their own visual tone. The third component is the error message. This one is reserved for when something goes wrong, like a network issue or an agent failure. Instead of a gradient bubble, we use a red card with rounded corners, so it stands out immediately and clearly signals that something needs attention. All right, now we build the actual screen composable. This is the one piece that ties everything together. It wires the view model, renders the chat, shows loading, and pushes user input into the agent pipeline. At the very top, we grab the view model using hilt, and we start collecting the state as compose state. This is what makes the whole UI reactive. The moment the view model updates anything, new messages, loading flag, input text, this composable recomposes automatically. Right after that, we set up a few UI helpers. A list state for our chat list, a coroutine scope for UI actions like scrolling, and a keyboard controller, so we can hide the keyboard the moment the user sends a message. Now here's the part that makes it feel like a real chat app. We add a launched effect that listens for changes in the message list. Whenever a new message arrives, we automatically scroll to the bottom, so the newest message is always visible without the user dragging the list manually. For the layout, we keep it simple and clean, a column that fills the screen. The top section is a lazy column that renders the whole conversation. It loops through the message list and for each one decides which UI to show. User message bubble on the right, assistant bubble on the left, error card in red if something goes wrong. This is exactly where those 3 message components we made earlier finally come to life. Now, if the agent is currently processing, we show a small typing indicator at the bottom. This is a Lottie animation running in a loop. It's a tiny detail, but it makes the UI feel alive. The user instantly knows the assistant is working and the app hasn't frozen. Finally, at the bottom of the screen, we render the input bar. This includes a rounded text field for the user's question and a send button. The text field is directly bound to the view model state, so every keystroke updates the state in real time. And when the user taps send, we fire the ask event, hide the keyboard, and that single event kicks off the entire agent loop you saw earlier. We have downloaded a public chatbot typing Lottie file, which we will put inside the raw folder. Since the last tutorial we updated a few dependencies, we need to tweak the place repository impl a bit so it compiles and behaves correctly with the latest setup. Make those small fixes, and then let's run the app and see it in action. Okay, launching the app, and yup, we hit an error. Classic. What happened? We forgot to annotate our view model with @HiltViewModel. Without that, Hilt can't create the view model properly, and everything falls apart at runtime. So let's add @HiltViewModel, make sure the constructor is marked with @inject, and rerun. Now the build is successful. Let's open the weather agent screen. Nice. We get the initial welcome message, so the UI is working and state is coming through. But the moment we type something, we still get something went wrong. And that's not a UI problem. That's expected because I haven't added my OpenAI API key yet. The agent can't call the model, So it fails and we drop into our error message flow. So let me add the API key, rerun the app, and now we're good. Now we can actually test some real inputs.